Mathematical analysis relies on a recurring toolkit of foundational limits, allowing us to evaluate complex expressions without returning to first principles every time. Our baseline is sequence A, the limit of 1 over n to the power of p. Here we can see the behavior of 1 over n squared, and n cubed as n approaches infinity. As the power p increases, the sequence collapses towards 0 at an accelerated rate. This provides a clear, simple standard for convergence. We use these simple baseline rates as reference points when we encounter more complex sequences where multiple variables are in conflict. Sequence B tells us the limit of the nth root of a constant is 1. Intuitively, an infinite root compresses any positive constant down to 1, regardless of its starting value. To prove this for p greater than 1, we set the nth root of p equal to 1 plus a small positive difference, xn. By showing that xn must shrink to 0 as n increases, we confirm the limit. Sequence C presents a friction point, the nth root of n. Here, the base is growing toward infinity, while the exponent is shrinking toward 0. If we test this numerically, we see the output values for 10, 100, and 1000 converging toward 1. The shrinking exponent eventually dominates the growing base. We prove this by setting the sequence equal to 1 plus dn and applying the binomial theorem. By isolating the n squared term and dropping the rest, we create a mathematical trap for the variable dn. Isolating this specific term is a deliberate method used to force dn to 0, providing the rigorous proof that the limit is indeed 1. Sequence D compares a polynomial numerator to an exponential denominator. This racing graph of n cubed versus 2 to the power of n shows the golden rule of analysis: exponentials always grow faster. For the formal proof, we pick an integer k larger than the polynomial power alpha and unpack the binomial expansion of the denominator. This kth term in the denominator suppresses the n to the alpha in the numerator. This leaves n variables only in the denominator, which drives the entire fraction toward 0. Pause the video here and use the logic of competing infinities to prove sequence E. The limit of x to the n is 0 when the absolute value of x is less than 1. To solve this, look at sequence D again. If we set alpha to 0, the numerator becomes a constant 1. Then we let 1 plus p equal 1 over the absolute value of x. This maps the expression directly onto our previous proof. Because the dominance of the exponential term is already established, evaluating variable sequences like this becomes a process of identifying which theorem to apply. These 5 special sequences function as a cheat sheet, allowing you to identify convergence without repeating proofs. They lead to the ultimate hierarchy of growth. Logarithms grow slower than polynomials, which are overtaken by exponentials, factorials, and finally n to the power of n. Internalizing this ranking allows you to predict the behavior of almost any sequence by simply looking at its components. These limits provide the starting point for proving the convergence of series and the behaviors of continuous functions in the